can get me a bottle of water? Okay. Yeah. We start. Good evening, everybody. Welcome to this live session, the first live session in the rerun course of Point-Set-Topology Part 1. You are all aware that the session is sorry for that. I think now it's okay. So the session is interactive session, namely to solve any kind of problems you may have or you already have in the course. So right now, course has taken already 2 weeks of time, right? So something like 10 lectures you had already. So whatever is covered, even those portions we can discuss. If you have some other generic questions also about the course, how to study, etc., all those things you should talk first. So you should post your questions and then we will respond to that. Okay? Yeah, welcome now. So I can see two of the students, name of the two of the students, Mani Chaturvedi and Saqib Muhammad. Good evening to them. So if you have your questions, please start typing them. Mani wants to speak. I think you cannot speak. That is the problem. You have to post. If at all, in Hindi also, you have to type and then if possible, I will try to answer in Hindi. Hindi में हम बोलना मुश्किल हो जाएगा. But what is the question? How do you prove? How do you define a continuous map, etc.? It will be difficult for me, no? Hmm. Yeah. So let me see what is the query. Sadiq Muhammad, there is a, uh, he says there is a good book and so on. So what is good book? What is good book for this course? That is the point. For this course, uh, the way it goes, my notes is the best book for you. Otherwise, you will have to keep searching for where to look for the materials. Okay. There is not many or any perhaps new, there is nothing new as such, I might be saying, but the way I say things and the sequence I have put this material, you will not find it anywhere else. But you have my notes also, right? So you can have that also. And Mani makes a comment here. There is hardly anything for me to reply. I just want to emphasize his comment. You are most welcome to learn this way, namely not just exam-oriented way. And this is precisely NPTEL courses, especially my course, is meant for that. Okay, your exams and all these tutorials or whatever you have, submissions, that is only to measure yourself, how much you have understood. It only helps. If you don't need it, you don't have to worry about that. Okay. Of course, you want a certificate from NPTEL, then you will have to do all that exam-oriented studies. Okay, you have to submit your assignments and appear for exam and so on. You are most welcome to learn without that, no problem. Mohammed again wants me to tell the motivation and the purpose of this course and so on. So that is like the praise in point set topology is what I have to do. I have done it several times every day, almost. Topology as such arose in the study of more difficult or more natural problems in analysis, especially in complex analysis, wherein the domain of the subject for complex analysis is the two-dimensional plane. Whereas if you start with real analysis, it starts with the real line. The real line has a lot of structure, okay, though it is very thin as such, which the complex line doesn't have. On the other hand, the complex plane, the two-dimensional plane, has much more richer in structure in a different way. Something what is common to both of them, what is not actually the geometry involved in the plane, okay, but something somewhat common to R1, R2, R2 means R cross R, R cross R cross R, and so on, if you go further. Okay, what is common to all these things, in a very heuristic way, you can say is topology. Okay. many problems in topology arise out of geometry. But within geometry, if you stay within geometry, you may not be able to even understand what is going on, let alone solve them. This is usually the case in life also. A person who is totally involved in a particular problem may not be able to solve it at all, because he is a part of the problem. It requires somebody to stand out, or somebody else who is not at all attached to these things to solve that. Especially psychological problems are like that, right? After all, mathematics is full of mind game after all. So this analog that I have given you from the day-to-day life, that is necessary. For example, one of the problems in measures, about measures, about Riemann integrals, functions, integrability of a real valued function of a real variable. That problem was solved by introducing the notion of measure in a general way by Lebesgue, what's called as Lebesgue measure. Okay. So the volume, the line length becomes a special case of the measure there. And you have to understand Lebesgue's theory to solve that problem. The problem can be stated without Lebesgue theory, namely, you take any function, then what can you say about the volume or the set of all points wherein the function may be discontinuous, so that it is still integrable. The function is integrable. An integrable function, how large can be the set of discontinuities? So that problem was solved by Lebesgue method. Similarly, hundreds of problems in geometry make sense only when you go to topology. That is only a small picture of topology. The topology is not just that. But why I am telling this one? How it arose, what the motivation. For example, you may be presently there is a big news about in topology. Topology seems to be dead and so on, but once in a while, maybe once in 2 years, 3 years, topology will be again in big news. A couple of years back, very elementary theory as far as topology is concerned was used by physicists who got Fields Medal, who got a Nobel Prize. By using the topology, they could solve some difficult physics problem. And recently there is something about the knots, something whether a slice knot is a ribbon knot or not. So such things are there. Though topology as such has become very, very mature and somewhat very difficult, not easy new things again and again are proved today. It has become quite tight. It's for that reason, because it's a very mature subject, it is being used by everybody in all sciences. This course cannot go to that level. It is part one I have told you. Even part two cannot go to that level. I have given two more courses, namely under the algebraic topology. They are also part of topology. What is the purpose of this course is that you will be able to follow part two and part three. That's all. Okay. So you cannot in a single day become an astronaut or something. You will have to first do a lot of exercise, elementary exercise, including learning certain languages apart from many other, physics, chemistry, and so on. So it's like that. So let me see whether there is any other questions directly related to the material. One can have two different pictures. Okay, Sushil Singla has posted some question. This question is about uniform continuity opposed to ordinary continuity. Once again, the answer is there in whatever I told you, the origin of topology in the beginning. It is directly from where? From analysis. Okay. A simple-minded application of uniform continuity comes in the following, namely, take a sequence of continuous functions. Okay. Take a sequence of continuous functions which converges. Just if you take pointwise convergence, the limit will not be a continuous function, need not be a continuous function. So you got uniform limits, first of all. So uniformity in the sense of the limits. Now, continuity, uniform continuity is a slightly different concept. Okay. What is that? Continuity, remember, is local. Okay. For each point, you have something, right? So when the things are becoming larger and larger, namely from one point, you have some control, 2 points, you have some control. As soon as you have finite limit, all these controls can be taken into one single control. The control being finding a common epsilon, one positive. Okay. So epsilon 1, epsilon 2, epsilon. If you have finitely many of them, the minimum is also a positive number, a finitely many positive number. Minimum makes sense. That's also a positive number. The problem starts as soon as you have infinitely many positive numbers. The minimum as such does not make sense, perhaps may not make sense. What makes sense is infimum. But infimum of a positive set of real numbers may not be positive. Okay. So that is where the difference starts. If that is positive, then once again, you have a uniform continuity. That minimum becomes infimum, infimum becomes minimum. Okay. That's a positive number. That will take care of all the points simultaneously. Okay. So we start, what is the criteria? What are the happy situations? What are the conditions which will guarantee that? Now, this will come to now instead of points, you just re-examine the definition of continuity. At each point, you have a neighborhood. So the moment you have some epsilon 1 around that point, that epsilon 1 will work for in a small neighborhood, right? Therefore, we get finitely many neighborhoods. Those the points themselves may not be finite, but if finitely many neighborhoods are covered by finitely many of them, then we are done. And this is where the compactness enters into picture. If the original space is compact, namely from arbitrary cover, you can always come to a finitely many cover. So that is how compactness was coming into picture. And uniform continuity and compactness go together, hand in hand. Okay. One more part of this question is why you need uniform continuity. So there are many situations. I will leave this one to you. You can, in the course itself, you can find out a lot of examples wherein uniform continuity is necessary to conclude anything about limits. The question is why uniform continuity considered this one? This is just purely logical. There is the condition itself is stronger. Uniform continuity implies ordinary continuity, but ordinary continuity does not imply uniform continuity. You have seen example. That's all. That's all. One is stronger than that. Okay. So I think what the question though asked like that, I think I have answered the purpose of the question. Okay, why uniform continuity is needed and how it is studied in topology. Okay, by the way, all these come from metric spaces, but I have indicated in the courses that uniform continuity can be studied out of metric spaces also, without epsilon delta. But then you will need something called uniform spaces and so on. So question was posed by Sasankha or whatever, Sasankha Rubra. So thanks for Sasankha. When somebody asks a question, other people also get benefit, not only the person who has asked. So that is the beauty of these live sessions anyway. So any more questions from anybody else? Okay. So Nipurna Shakya wants to know how the concept T can be derived from AU and FI. I have almost forgotten what was T and what was AU and so on. Let me go to the concept so that everybody will get that. So, hi. Can you just tell me what lecture it was there? The TA from AU and FI, finite intersection property and arbitrary union. So what is T? So how do I scroll it? No. This one. Come here. Slide. Huh? Okay. Here, huh? This should work. Button. Huh. Six. I can't go there. Where is T? Ah. The axiom T, can everybody see it? Axiom T says that the total space X and the empty set are both members of this tau. AU says that if you take any subfamily of tau, then the union of members of this subfamily is again a member of tau. FY says if you take a finite subfamily of tau, then the intersection of all these finitely many members is again a member. Okay. So here you have to understand elementary set theory, namely, if you take an empty family, okay? Empty family is also a subfamily. Empty family, no members are there. Then its union over all those members is again empty. Okay. So AU already gives you empty set is there. All right. Now look at the intersection on an empty set. I think this is difficult for quite a few of you. The intersection on an empty set is the whole set X. So why is that? Let us take a general way what is the definition of intersection? So suppose if you have two members, two subsets of a given set X. X is a given set here. And tau is a subfamily of members of subsets of X, right? Or subsets power set of X, that is tau is a family. So everything is inside X. So take two members, A and B, two subsets. What is their intersection? Set of points which is common to both of them, right? A point must be inside this one, must be inside that one also, right? Similarly, if there is a whole family A belonging to, say, some lambda, it must be there in all of them. A point which is in each of them, a point which is in all of them, those points are put inside this intersection. Okay. Now let us take any arbitrary point of X. Okay, say X naught. Can we put it in the intersection? When can we put it it must be in all the members, right? That means if we cannot put it, means there must be at least one member which does not contain this point. That member must be in the given family. The given family is empty. There is no member there. So when you say there is one member, that is a contradiction. So you cannot find a member which cannot contain this point. Therefore, the two negatives like that. Therefore, x naught is a point of the intersection. So what I have shown? I have shown that each point of x is in the intersection. Therefore, x itself is a member of tau. So Fi gives you x is there and Au gives empty set is there. So that is the proof. Okay. You must know that similar things happen in algebra also. Take an additive group. Take an additive group. Okay. Take a set of points of the additive group. Let us say finite. Don't worry about it. Any finite means empty also. No? Fine. What is the sum? Sum makes, right? Finite sums make sense. Okay. What is the sum? You have to add each member of that subset exactly once to get that sum. Right? Now, if you take an empty family, what will be the sum? So this is where you have to use, set theoretic logic here. The sum on an empty set is 0. The 0 is the identity element in the additive group. Now, this may be easy for many of you, but when you put the same thing in the product structure, instead of writing additively, if you get product, then few people have problems there. It's the same thing. If you write products, usually one writes the identity element as with the symbol 1, just like what happens in the real numbers or rational numbers or integers. Okay. 1 is the identity element for the product structure, multiplicative structure, right? Product over an empty family is 1. Sum over an empty family is 0. If you are working with real numbers or complex numbers or any kind of, commutative ring. So in 12th standard, even in before 12th standard, you must have learned that any number raised to 0 is 1. The raised to 0 being indicating that, the superscript, their number indicating number of times you have taken 2 and multiplied. 0 means you have not taken, it's empty family. 2 raised to 0 is 1, right? That you have learned. So that is transcribed in this way in any commutative ring. This is true. Any number r raised to 0 is the identity element of that ring. If you take summation, it will be 0 element of that ring. Okay. Now, this Fida wants me to explain things using graph. Epsilon delta concept of continuity using graph. What this means, maybe he wants using picture. Okay, I am strongly against using pictures finally in the final running of topology. Okay, though pictures again are some kind of tools. Ultimately, you must get rid of the picture. Okay, you should use only the strong argument. All right. The more explanations you find in many books about the epsilon delta definition of continuity, the more confused you are. There are all sort of explanations. Like if something is very near, then the image will be very near and so on. All those words can be misconstrued, misunderstood. The only correct thing is in terms of epsilon and delta. You have to stick to that. Given epsilon positive and a point, there must be a delta positive such that all points y near x by the distance delta, that nearness has to be replaced. Word near should not be used. What is near? Why can't it be far? That is just an English concept, the English word. So x minus y modulus, that is the distance in terms of real numbers or complex numbers. So that is replaced by distance between x and y in the metric space. Distance between x, y is less than delta should imply distance between fx and fy must be less than epsilon. This is the definition. You stick to this one. The delta will depend on f, the given function, on your epsilon, as well as on the point at which you are discussing the continuity. So that is obvious, that need not be told, because the way the sentence is formed, first you have to take the function f. It is about the function. So everything that you say afterwards depends upon the function. Then you are choosing epsilon. Choosing, you are not choosing, it is given. You want that much of accuracy. That is the meaning of that. Okay. So nobody ensures that only for epsilon you put 1 or 2 or 3, it is good enough and so on. For all such epsilons, it must be possible. Given epsilon, something is possible. It's for all epsilon. Okay. The only thing about epsilon is that it's a positive real number. So delta will depend upon that. Then there is a delta. Then such things are decided. Okay, so it will depend upon the point x, the point f, the function f, the point x, and as well as the epsilon. What I would challenge you is, you want using graph, okay? You want, can you do it yourself? Try to do your whatever graph you want and send it to me. We can continue the discussion after that. In this session, I am not prepared for drawing things on blackboard and so on. The word graph itself has many meanings. So what is the meaning of that? You try to do it. You send your attempt, whatever you have tried. Okay, we can continue the discussion. Privately also, I will, if there is a more interesting it becomes, then we will put it in the next session also. Don't worry. Any more questions coming? Do you want to have some comments, Vida, on your own question after whatever I have heard from me? Hmm. So there seems to be no further questions. Let me add a small question to you based on your questions only, namely uniform continuity. I told you uniform continuity is a concept, especially from analysis. Okay. I would like to make this one very specific. It is not a topological concept, not as compared to continuity. Continuity is completely topological concept. Uniform continuity is not. For example, for arbitrary topological spaces, if you have function f from x to y and x and y are arbitrary topological spaces, there is no notion of uniform continuity. Secondly, the strongest concept, namely a homeomorphism from X to Y, both X and Y may be metric spaces. There may be homeomorphism from X to Y, which may not be uniformly continuous. Okay, I think this should completely demystify the concept of uniform continuity and continuity as such. We have not given much importance to uniform continuity in this course. Why? For this reason. It is not a purely topological concept. Okay. So now question is, find an example. There are easy examples of metric spaces X and Y and a homeomorphism from X to Y, which is not uniformly continuous. Yeah. So if somebody finds it, he can post it, we can discuss it. And if nothing comes out, I'll let you know in the next session. Once again, if you have any more comments or questions, you are welcome. Okay then. Thank you all for participating in this one. Let us thank the NPTEL team also for helping us. See you again in next time. Thank you.